problem on conservation of angular momentum. See, this momentum has to be conserved, or the angular momentum of a system about a particular axis can be conserved only when there is no external torque on the system. In the absence of an external torque about a particular axis, the angular momentum of the system can be conserved about that axis. So, let us read the problem and see how we can use it to solve the problem here. A thin circular ring of mass capital M and radius capital R is rotating in a horizontal plane. See, in all these rotational motion problems, I think we will have to be very clear about what is the plane of rotation and what is the axis of rotation. So, here the ring is rotating in a horizontal plane like this. So, this is the ring and the axis is vertical and passing through the center. So, this is the axis. So, if you consider the ring to be like this, parallel to the floor, the axis is perpendicular to the floor and passing through the center of the ring with an angular velocity omega. So, that angular velocity is given. Now, if two objects of mass m each are attached to the opposite ends of the diameter gently without disturbing much, the ring will rotate with an angular velocity of how much? See, why should the angular velocity change here? No doubt he has asked and all the options are there. None of them is no change or 0, right, or the original value. Is there any one as the original value there? No, all of them are different from omega, fine. Okay, so the angular, the question is, why should the angular velocity change? See, for the conservation of angular momentum, the angular velocity must change because you have already changed the moment of inertia. How do you write the angular momentum of a body? The angular momentum of a body is written by the formula I omega. So, I omega was the original angular momentum, where I was that of a ring, which is mr square, and omega was the angular velocity you had given. Now, you attached two objects of mass m each at the opposite ends of a diameter and changed the moment of inertia. For the angular momentum to be conserved, the angular velocity must change. So, now we will try to find out the new angular velocity. I will write new moment of inertia into new angular velocity, that is new angular momentum as I1 omega 1. I1 is nothing but mr square plus those two masses which you have added at the diametrically opposite corners. See, I am writing the moment of inertia about the axis, about which your original ring was rotating. I have not changed that axis. So, mr square is the moment of inertia of the ring about that axis, and small mr square of one of the masses, another small mr square of the other mass. So, totally it makes 2 mr square into omega 1. Now, if the angular momentum is conserved, I omega should be equal to I1 omega 1, and that helps you solve to get the value of omega 1. And omega 1 will be, r square gets cancelled, m divided by capital M plus 2 small m into omega, and that makes your which option correct? M omega divided by m plus 2m. The first option is perfectly correct. Right? I hope you understood this, but please remember, angular momentum can be conserved only in the absence of an external torque about the given axis. We have one more problem on conservation of angular momentum, but I think it is slightly one step ahead. He wants you to write down even the rotational kinetic energy also. A circular disk of moment of inertia I1 is rotating horizontally with velocity omega 1 about its axis. So, this is the disk, this is the axis, and it is rotating with an angular velocity of omega 1. Another disk of moment of inertia I2 is dropped coaxially on the rotating disk. So, this was the original disk, and one more disk is going to be dropped on top of it coaxially. So, which means the axis of rotation for both the disks is going to be the same. The second disk is initially at rest, but eventually starts rotating with the other one with a common angular velocity. The final energy is to be written. So, naturally what will happen? One disk is already rotating and you will put one more disk on top of it. So, initially that may be at rest, but because of friction it will also start rotating, and finally the relative motion will cease. friction will become static and both will have a common angular velocity. Initially the friction is kinetic, right, but finally the friction becomes static and both will have a common angular velocity. So, we will first try to find out that common angular velocity and then write the final energy. Okay. So, I will conserve the angular momentum. I1 omega 1 should be equal to I2 omega 2. But what is I2 here? I2 is I1 plus I2 and the angular velocity is omega 2. I hope you agree with this, because initially you had only one disk and now you have two disks on top of each other. So, moment of inertia has to be added because it is a scalar quantity. So, into omega 2, that gives you omega 2 as I1 omega 1 divided by I1 plus I2. Fine. So, this is the new angular velocity and now you are supposed to write the kinetic energy. And how do you write the rotational kinetic energy? The rotational kinetic energy is given by half I omega square. Fine. So, I will write half, I means I1 plus I2 because there are two disks which are rotating and the common angular velocity that we have found out is omega 2. So, I1 omega 1 divided by I1 plus I2 whole square. So, that makes 1 I1 plus I2 getting cancelled and the answer is I1 square omega 1 square divided by 2 into I1 plus I2. I hope you understood this. We first conserved the angular momentum and find out the new angular velocity and we found out the new angular velocity and now we have written the rotational kinetic energy finally. So, the correct choice here is B. So, option B is the answer. So, here is one very conceptual problem again. See, it's why I call it to be conceptual is it's not a direct question. He has asked you something, but it means something else, right. See, there are point masses m1 as well as m2 which are placed at the opposite ends of a rigid rod of length L, but negligible mass. So, this rod does not have any mass, but the length is L and there are two masses m1 and m2 point masses which are kept at the end points. The rod is set rotating about an axis perpendicular to it. So, perpendicular to the length of the rod. So, the rod is set rotating. The position of the point on the rod through which the axis has to pass so that the work required to set it rotating at an angular velocity of omega should be minimum. So, this is the question. So, why I called it as conceptual is he has asked you to find out point on the rod through which you have to consider the axis so that the work that you are required to perform in order to set it rotating at an angular velocity omega is minimum. You have already decided to make it rotate with an angular velocity of omega, but the amount of work or the energy that you are supposed to spend in order to make it rotate with that angular velocity should be minimum. Now, how do you write the energy or work done is basically the energy that you will be providing that rod. So, it will be half I omega square. Omega you have already decided. So, now in order to make your work minimum, the moment of inertia that you are going to consider should be minimum. And in the previous problem also I had told you once that the moment of inertia is going to be minimum only when the axis is considered to be passing through the center of mass. So, indirectly he has asked you the position of the center of mass of this system. Fine. So, what we will do? We will use the formula and write down the position of the center of mass. What is that formula? xcm equal to m1 x1 plus m2 x2 divided by m1 plus m2. Fine. But where are these x1 and x2 to be taken from? From the center of mass. So, if you imagine this axis to be already taken passing through the center of mass, I will write the x coordinate of the center of mass to be 0 and use the formula m1 x1 plus m2 x2 divided by m1 plus m2. See, 0 is equal to, this should be basically xcm equal to, but I am writing it as 0 is equal to m1 x1, m1 is m1 and instead of x1 I am writing minus x, m2 x2, m2 is m2 only and x2 is L minus x, divided by m1 plus m2 is m1 plus m2. See, xcm equal to m1 x1 plus m2 x2 divided by m1 plus m2 is the formula. But I have written 0 because this x coordinate of the center of mass is being measured from the axis of rotation. So, that itself is the center of mass. So, x coordinate is 0. Okay. Why is that I have written minus x here? Because it is on the left side of your reference, and that I have written as positive because it is on the right side. Now, if you solve this, you get the value of x as m2L divided by m1, but if you want I can solve it and show you. So, m1x, m2x, that is m1 plus m2 into x, m1x, m2x. So, m1 plus m2 into x is equal to m2 into L, m2 into L. So, x is m2L divided by m1 plus m2, which makes option C as the correct one. I hope you understood this. X is m2L divided by m1 plus m2. That is the answer. I would love to take one more beautiful problem on conservation of angular momentum, but the purpose is to warn you that whenever you are planning to conserve the angular momentum, the velocities that you are going to take should be absolute and they should never be relative, right. So, please remember this. Let us see. A circular platform is mounted on a frictionless axle. The radius of the platform is 2 meters. The moment of inertia of that platform about the axis is 200 kg meter square. It is initially at rest when a man of mass 50 kg starts walking along the edge with 1 meter per second with respect to ground. So, this is very, very important, because had this speed been given with respect to the disc, then we would have converted it into with respect to ground, because I told you while conserving the angular momentum, we need the angular velocities which are absolute, which means with respect to ground, not with respect to disc. But fortunately, he has given that he starts walking along the edge with 1 meter per second with respect to ground. Fine. Time taken by the man to complete one revolution is to be found. So, initially everything was at rest. The circular platform was at rest, the man who was at the edge of the disc was also at rest, but the moment he starts walking, in order to conserve the angular momentum of the whole system consisting of that platform as well as the man about the given axis, the disc itself will start rotating in the opposite direction. If the man starts walking anti-clockwise, the disc will start rotating in the clockwise direction. Of course, we will confirm that by conserving the angular momentum, but that is how the theory goes. Fine. So, what I will do is, I will first try to find out what is the angular velocity with which the platform will start rotating when the man starts walking with a speed of 1 meter per second. Okay, why is that important? Because he has asked you to find out the time taken by the man to complete one revolution. And let us not forget that to complete one revolution, it is not just his velocity alone, but his velocity with respect to the platform, which is important. Because I have started walking in one direction, platform itself has started rotating in the opposite direction. So, definitely had the platform been non-rotating, then definitely I would have taken much more time to go around the circle once. And because the platform is also rotating in the opposite direction, I think I need less time to finish one revolution. I hope I have spoken very clearly. Now, let us see how to conserve the angular momentum and find out the angular velocity first. So, initial angular momentum 0 and final angular momentum of that man is to be written as r cross p, right. Please remember, man is a particle here and his angular momentum about the axis should be written as r cross p. So, r is 2 meters and p is his mass into the velocity with which he is moving, that is 1. Fine, that is the absolute velocity, plus I omega, which is I omega is for the circular platform. So, 200 into omega 1. Omega 1 is the new angular velocity with which the platform has started rotating. So, if you solve this, you get omega 1 as minus half, right, radians per second. Okay. What does this minus indicate? It just indicates that if the man is walking in one direction, the platform has started rotating in the opposite direction. And what is the angular speed? Half radians per second. Okay. Now, what I will do is, I will try to find out the relative velocity of the man with respect to the platform. Let us not forget that the man has started walking on the edge of the platform. So, I want to find out the linear velocity of a point on the edge of the platform using the formula V equal to omega r. So, V equals omega, which is half, and r, which is 2, and that makes it 1 meter per second. So, this is the point on the rim of the platform, right? This is the velocity of the point on the rim of the platform. Now, this is where the man is walking, and his absolute speed is 1 meter per second. So, velocity of the man with respect to the platform is velocity of the man minus velocity of the platform, right? Velocity of the man, which is in one direction, I have taken it as positive, and that is 1, minus velocity of the platform at the point where the man is walking is also 1 meter per second, but it is in the opposite direction. So, that makes it 2 meters per second. So, what is the relative speed with which the man on the edge of the platform is walking with respect to the platform? He is walking with a speed of 2 meters per second with respect to the platform. And therefore, in order to go round once, which is basically like travelling a distance of 2 pi r, which is 4 r, sorry, r is 2, so 4 pi. So, 4 pi is the distance he is supposed to cover, 2 meters per second is the velocity with which he is moving. Therefore, the time taken is going to be t equal to 2 pi r, which is 4 pi, because r is 2, divided by the speed with which he is walking is 2 meters per second. So, distance by speed is nothing but 2 pi seconds, and that makes your option D as the correct option. I hope you enjoyed this problem. See, it was basically conservation of angular momentum first. So, we conserved the angular momentum, and here I warned you that had this velocity not been given with respect to ground, then we would have first converted it with respect to ground and then used conservation of angular momentum. Okay, but we were saved there. So, we got omega 1. This is the new angular velocity with which the platform will start rotating. And then I have found out the linear velocity of a point on the rim of the platform, because that is where the man has started walking. I have used the formula V is equal to omega r. Omega is half, r is 2, so that makes 1 meter per second. And what does this minus indicate? That the platform has started rotating in the opposite direction. So, now I will find out the relative velocity of the walking of the man with respect to the platform. Please remember, man has started walking, platform has also started rotating. So, Vm minus Vp. So, Vm is 1, which I have taken as positive, minus Vp is another minus 1, because it is opposite. So, that makes it 2 meters per second. So, this is the relative speed with which he has started walking, and with this relative speed with respect to the platform, what is the distance he is supposed to cover? 2 pi r, which makes it 4 pi.